Hi and welcome to the video called Composite Functions Part 2. In the video, which we called Composite Functions Part 1, we just created composite functions without even considering the validity of the resulting functions. That is what we will consider in this video, for unfortunately it's not always possible to create composite functions based on two initial functions. That is what we will consider here. One way of showing what the composite functions are all about could be to illustrate it with one example, which is exactly what I have decided to do. The example which I will look at consists of a function fx, which is defined as the square root of 2x minus 6. We also have yet another function gx, which is defined as 3x plus 7. So the two potential composite functions we will be able to create based on these two initial functions fx and dx could be g of f of x and f of g of x. So now we'll investigate whether these two composite functions actually occur. The first thing which we need to do when we have to investigate for potential composite functions is to figure out what are the domain and the range of respectively fx and gx. So let's start with that. So step number 1 will be to find domain and range for fx and gx. Alright, let's start with fx. We see fx is defined as the square root of 2x minus 6, and as we recall, we're not able to take the square root of a negative number. Therefore, we need to make sure that 2x minus 6 is greater than or equal to 0. Which of course means that 2x must be greater than or equal to 6, and that we can of course simplify into x being greater than or equal to 3. So in other words, the domain for the function f is equal to all the numbers from 3 included to infinity. The square root of any certain number will always be positive or equal to 0. So therefore, based on that, we can conclude that the range of the function f must be all the positive numbers, including 0. So now we have figured out what the domain and the range is for the function f. We have to do the same thing for the function g, which is much easier actually, because we see here based on the expression that we have a linear function. So we can directly, based on that, conclude that the domain for the function g is equal to the range for the function g, which is equal to all the real numbers. Alright, so now we have done that, figured out what the domain and the range is for both fx and gx. So before we go any further, let's try to visualize what we're actually doing when we are creating a composite function. Let's take the example where we are looking into the potential composite function, which we call g of f of x. So what is it actually we do? Well, if you remember from the video Composite Function Part 1, we take our starting point in this function f, and then we insert that into the function g. That is, we take a certain x, which of course has to be part of the domain for f. And then we do with this x whatever the function expression f tells us to do. And that will of course leave us with a function value which has to be or will be a part of the range for f. And then, if you recall from the composite function, then what we do is that we insert f into g. So if you insert f into g, then you need to remember or be aware of that the range of f has to be a member of the domain for g. That is what we're illustrating here. That makes sense because recall that we insert f into g. So we need to make sure that what we insert here actually is a member of the domain for the function we're actually inserting it to. If that is not the case, then we could end up with a function value for f which is outside the domain for g, and then we cannot take it any further. So therefore we need to make sure that the range for f, oops, we just delete this small thing. The range for f must be a member of the domain for g for all axes which are domain part of the domain for f. That we have to consider, and that is the restriction, whether we are able to create a composite function or not. If this is not the case, if the range of f is not a member of the domain for g for all the axes in the domain for f, then we're not able to create a composite function. But if that's the case, then we can take it a step further. When we insert what we have here from f in g and do whatever the function g tells us to do, and then what happen here will be that we will end up in the range for the composite function d of f. Alright, so that is what we actually do when we create composite function, and based on this small drawing here we can see that the restriction in general will be if we are investigating for whether this composite function d of f is valid or not, then the range for f must be a member of the domain for g for all the axes which are part of the domain for f. Alright, if we take that into consideration, then let's go back to our example here to see if we actually can create these two potential composite functions based on this f of x and this gx. Okay, I will just delete the small drawing here. So, okay, so let's go back to our example and see, okay, let's start by investigating for whether the composite function d of f really exists. That's what we're investigating for. That's our question. If that should be the case, if d of f should exist, then we just agreed that then the range for f must be a member of the domain for g. Alright, so we'll look into the range for f up here. We have figured out that that is all positive numbers equal 0, including 0, all positive numbers including 0. That is the range for f, and that has to be a member of the domain for g. Domain for g is equal to all real numbers. All positive numbers including 0 is a member of the all real numbers. So therefore we can say yes, we do have, based on this we can say yes, we do have a composite function called g of f of x when we have these two initial functions given. So now the final thing is just to figure out what is the expression for g of f of x. That's no problem. We remember what we looked at in the video part 1. We insert what we have for f, which is the square root of 2x minus 6, into g. So that is 3 times the square root of 2x minus 6 plus 7. So that is the expression for the composite function g of f of x. Alright, let's also consider and see if the other potential function f of g of x, does that exist in this example here? Based on our visualization, we could see that if that should be the case, then the range for g must be a member of the domain for f, which in this case we are inserting the function g into f. Alright, so let's jump up here and see what is the range for g. That was all real numbers. What is the domain for f? That is the numbers from 3 to infinity. All real numbers not a member of the numbers from 3 to infinity. So based on that, we can see that we don't have a potential, we don't have the composite function f of g of x with these two initial functions given. So f of g of x does not exist in this example. Alright, so let's just finally go into an overall conclusion that if we're given two continuous functions f of x and g of x, then we can create the composite functions, the composite function g of f of x, if the range for fx is a member of the domain for g for all x's being a member of the domain for f. That's the restriction which we have to consider if we should investigate for potential composite function. That was all for now. See you in the next video.